Okay, welcome everybody to this workshop put forward by the American Ceramic Society entitled Tools for Visualizing and Understanding the Structure of Crystalline Ceramics. My name is Taylor Sparks, and I'll be your instructor for this class, and I'm just so excited to talk to you guys about these tools. If you joined a little bit later, I was just talking to the guest saying how I wished I'd known about these things earlier in my career, and so I'm passionate about making sure that people can learn about them as easily as possible now. Um, we have 3 days and an hour and a half each day, which is not a lot of time. So I'm going to be a little bit brief on some of the pedagogical parts and spend a little more time actually demonstrating and showing how to use these tools. Um, these are being recorded, and I have additional tutorial walkthroughs online, which will be linked as well. I'll show you the links to those in a moment. So I'd say where we have time, you can feel free to ask questions. You can interrupt because there's additional videos that we can refer to. So I think it would be really great to have engagement and dialogue and questions. So if you're confused on a step, you can chime in. If you'd like to follow along yourself with the refinements, you can also do that. I'll show you how to do that in just a moment. Um, but if you don't capture everything in this, 3 days, hour and a half each, that's only, not very long. You can also feel free to reach out to me, and I'm happy to do one-on-one, consultation to explain how to do things at no charge as part of the course fees. I think you really getting you up to speed. So feel free to use me as a resource going forward, even if we don't cover everything today. That said, let's go ahead and get started. I'm going to hide this floating thing so I can see what I'm doing. Okay. So I'm at the University of Utah in the Material Science and Engineering Department. I got a job here back in 2013. So it's been a minute since I've been here. And before that, I was a PhD student at Santa Barbara and Harvard. Okay, let me jump ahead. So here's what we're going to cover today. Today I'm going to talk about what even is Rietveld refinement. What does it do? How does it work? I'm going to then give examples of how we can use it for quantitative analysis of multi-phase mixtures. So if you've got a mixture of powders and you know that there's some silicon and some alumina and whatever else in there, can you actually refine out the weight fractions of those different phases? Yeah, you can. And you can even capture amorphous content. So we'll talk about those things. Then I'm going to shift gears and talk about how you refine details of individual phases, things like lattice parameters, atomic position, site occupancy. We will shift gears and talk about thermal displacement parameters, preferred orientation, and then crystallite size and strain. But before we do any of that, I do want to have you guys be downloading something right now if it's convenient. If you plan on following along, there's 2 bits of software that you might consider downloading. The first one you should for sure get, which is GSAS. GSAS is there's many different softwares out there that can do Rietveld refinement. Heck, you can do it if you want. You can do it in Excel. I don't recommend it. GSAS is great. It was developed by Brian Tobey and others at Argonne National Laboratory in the Advanced Photon Source. There's reasons why I like it over all the others. The main one is it's really good. It can do all the things you want it to do, and it is free. It is open source. So huge kudos to them because there are paid versions of software, things like Topaz and Expert High Score, which are amazing, but they are very, and I would say even prohibitively expensive for a lot of people to use. So the fact that there's a free version, GSAS, out there should really be celebrated. There's other free ones like Full Prop and that, but in today's demonstration, we'll be using GSAS. So let me show you where you can find that if you're interested in following along with that. There's a link I'm going to drop in the chat right now. That will take you to the Git website for this GSAS page. So if you go here and then you click the top, like the home or whatever, you'll see lots of information about the software. The one that you probably want is just right here, this very first one, the installation options. And it will have options for, whether you use Windows or Mac. It's very simple to use. I was able to get it downloaded. I did a reinstall last night just to make sure it worked fine for me on my PC machine. And it takes just a couple minutes. So I would recommend that while you're listening right now, maybe now's a good time to pop over here and get the installation started while I'm talking about some other things, so that when we jump over to the practical component of today's class, you'll be able to follow along if that's what you'd like to do. The other bit of software that I'm going to drop in the chat comes from this group I actually forget what university they're at, but it's called PowDLL. So I'll put that in the chat real quick. And this is amazing software, which somebody puts together that allows you to convert different X-ray file formats to one and another's format, because they are usually proprietary formats, which is super annoying that these companies don't have a single open format that they use. But there's this software, PowDLL, which will allow you to convert them back and forth so that you can get it into a format that GSAS will be able to work with. So this is really great software. Both of these are free to use. There's no fee or anything. I think they have like a buy them a coffee sort of thing if you want, if you feel so inclined, but it's not required. Okay, so let's jump back over to our slide deck. If you want to have those downloading, great. If you want to just follow along, that's also fine. After all, these videos will be recorded. You can always follow back later or follow up with me at another time. Okay, so those are the softwares we're going to use. So what is Rietveld refinement? It was invented by Hugo Rietveld way back in 1969. And essentially what it is a quantitative refinement tool where in essence, what you're going to be doing is you're going to be calculating an X-ray diffraction pattern, and you're going to be comparing that to some actually measured pattern. And then you're going to be updating your model to make sure that the model actually fits the actually measured pattern. So for example, you might get something like this. You will have an actually experimentally measured data set. That's like the black data points here. If this is your first time seeing X-ray diffraction, it's probably not, but you know that it's intensity plotted as a function of diffraction angle to theta, and these peaks are indicative of where you have Bragg scattering happening by satisfying the Bragg's law. And they're not like perfect line functions. There's some broadening that comes from the instrument and other things related to the size of the particles. But the cool thing that I want to point out in this slide is take a look at this simulated pattern. There is some crystal structure. I don't know what this exact example is, but you can simulate what the pattern would be, and you can see that it matches pretty well. Now, if in the simulated pattern, the lattice parameter had been wrong, too large or too small, these peaks would be shifted in the wrong spot. But in the process of Rietveld refinement, you can update what the values of the lattice parameter and all sorts of other parameters, occupancies, thermal displacement parameters, you can update those in real time to figure out what is the actual structure that's giving rise to the experimentally measured spectra. Okay, so it's really about fitting a model to data. That's really what this is. It's a variable model. There's lots and lots of parameters. I'll show you in a couple slides all the different things that we can mess with. It does a least squares refinement. And then it also has the ability to account for errors that might have occurred during the measurement itself. If you're unfamiliar with X-ray diffraction, you typically have a diffraction plane, and you have to have your sample centered right at the apex of that plane. But if your sample's too high or too low, for example, that will induce an error. Or if your goniometer, you think that you're exactly at 90 degrees, but in fact you're shifted, it's actually 88 degrees because there's an internal problem in your instrument. That would be called a zero error. We can account for both of those because those are both really common, and other errors. In the Rietveld process, it's possible to actually account for those and correct for them, which is nice. And then lastly, there's a difference between what we're going to do today and what's called Labai or poly or profile fitting. And the main difference there is that in those ones, you're able to get the crystal unit cell, but you will not be able to get the other information, things like occupancies or thermal displacement parameters, because you release the requirement for it to fit the intensity correctly. You just are forcing it to fit the position correctly. More on that in a moment, okay? So when I said that you're fitting data to a model, this is the model, and it's really gross. So don't worry, I'm not going to spend a ton of time here. Really quickly, while I'm thinking about it, I do have, for all these values, all these variables in the equation, they're all defined here in my notes. And the notes are made available to you guys at my GitHub page. I'll drop a link to this if you'd like in the chat as well. You should have gotten it from an email from Greg, but you've got it there as well. In this GitHub page, all of my slides are available. So right here, if you go to slides, here's like my PowerPoint file that I'm using, or I've converted that to PDFs if you'd like to follow along. Later on today, I'm going to show you how to do step-by-step what to do, and these steps are found here. So in other words, you don't need to be like desperately trying to write things down, because everything you're going to see here, you have access to through this GitHub site. And because it's GitHub, this will be around archived and for you guys to use. I've also got links to the YouTube tutorial. If after the fact, later at another day, you want to follow up, you can follow along with the YouTube video. And then finally, we've got some examples we'll be going through. So if you're planning on following along, jump over to this link and you can download these files. If you haven't used GitHub before and you're like, I don't know what I'm even looking at, that's okay. It's pretty easy. You can download this entire thing if you want. You can just come over here and you could just download the whole thing if you want as a zip folder. All of those folders will get put on your computer. Or if you're familiar with using Git, you could clone the repository or whatever you want. But where you see this green code button, download zip is probably what most of you will probably want to do. Or if you want to download things one at a time, you can just click them, right? If you just want, like in the Lab 6 example, if you just want the Civ card, you can download the Civ card, and there it is. You'll be able to download that file if that's what you so choose. Okay, so more on that, and feel free to interrupt me at any time if you're like, I don't even know what you're talking about or how to do this, and I'm happy to slow down and explain things better. But let's come back to this for a moment and talk about what we're actually fitting to our model. Essentially, what we want to be able to do, if you look at the measured data, the measured data is showing you an intensity on the y-axis as a function of 2 theta for some diffraction wavelength. In this case, they're using copper K alpha as the radiation source, and it's plotted as a function of diffraction angle. So here we have the intensity, that's what we're going to try and simulate as a function of our angle 2 theta, but then there's all these other parameters, right? Now, I would say for this tutorial today, it's not critical that you know what all of these things are. If you have questions, I can point you to some great resources online or textbooks where it gets into them. But just realize that this is not something that you would want to do in Excel, because you would have to have this whole expression. And some of these things have equations themselves, like the capital F HKL, that itself is equal to the structure factor, which you have to calculate from this kind of nasty equation, which is based off of the atomic positions. Or like this small f, where is it? Small f is right here in the structure factor equation. It itself is equal to another complicated expression, which is shown graphically here on the right. All this to show you is just to point out how really valuable this GSASS software is, because it takes all of this complicated modeling and puts it behind the hood of a really nice GUI, a graphical user interface that we can interact with, that makes the process pretty effortless. So I could spend this whole 3 days just talking about the mathematics of what's going on here in the physics. But since this is an applied class, I'm going to skip that, and feel free to follow up with me later if you want to understand the more fundamentals of how diffraction works. Instead, we're just going to talk about how we model it in this workshop. Okay, one of the first things you'll notice is that the small f, it's for the anomalous scattering factors. And what is this? Well, this is the fact that depending on your radiation source and the material that you're investigating, they might interact in different ways. And I've got an example shown here with 2 different plots using this free F prime software, where in this case, we're looking, let's imagine you had some iron powder that you were investigating with the X-ray diffraction tool, okay? You're trying to figure out what's the structure of this iron powder or this compound containing iron. Well, if you use copper, which is the most common X-ray source, you can see here that the vertical line right here, the red lines represent the absorption spectra for iron, and this vertical line represents where copper exists at. And you see that it intersects up here. That means that it's going to have a very high absorption. And maybe this is familiar to some of you. If you've ever tried to do X-ray diffraction using a copper source and an iron-based sample, you get a really high background radiation, which is going to it's going to mess up your analysis, right? You can see examples of this. Let's hop over to the internet and look for one real quick. Iron absorption, XRD, copper. Let's see what comes up. If you look at this, you typically see really ugly backgrounds. Let me see if I can find one. So I don't know which ones are listing with copper, but you'll see a background which is just really high. This might be a decent example. The difference between the intensity and the background, like the most intense peak at 800 and your background at 200 is really high. This is likely because of absorption, right? And so that's not ideal. If you have really small peaks, you won't be able to see them because this background is too high. So the way that we get around that is you can just pick a different X-ray source. In this case, for example, if you switch to what's selected here, trying to read this. Oh, now it's using chromium. If you're using chromium, look, it doesn't absorb hardly at all. So when you guys are using X-ray diffraction, hopefully you're aware of whether or not you're going to get an undesirable anomalous scattering factor. And then if it's possible, if your machine can swap out the anode, switch from copper, which is the most common, to molybdenum or chromium or silver or some of these other different ones that are available. Okay, but that said, by far the most common thing that you're going to have is a copper radiation source. So we have the ability to model the intensity at any different 2 theta value for any different materials that we are investigating, both based off of the radiation we're using and the elements that we're investigating. So the next thing, if we look at what we're trying to fit here in the simulated pattern, these are basically like delta functions. They're pretty much like straight lines. But that doesn't match reality. In reality, these peaks have some width to them, right? There's some broadening. They're actually um, they're sort of peaks as opposed to delta functions. Therefore, we need to be able to model the shape of the peaks that we would expect to see. In a perfect world with point sources and everything lined up perfectly, it would be a delta function. But in reality, we have limitations on the optics of our instruments. And so there's some broadening in the peaks. And the broadening can be modeled 2 different ways, typically, as a Gaussian shape or a Lorentzian shape. So that first Gaussian profile, it's not exactly a Gaussian function, but it's similar to one. It has less what we call tails or shoulders. It's more, it takes up less overall space, whereas the Lorentzian has more broadening at the base. And you can actually combine these, right? There's different profile peak functions that you can use in the software that allow you to account for the shape that your instrument is generating. And I'll show you how to do that when we get to the software. It's through functions like this, where this will actually create that sort of Gaussian shape. And depending on the U, V, and W parameters, which are just fitting parameters, you can kind of make it fit all sorts of crazy profile shapes. So more on that in a moment. But that will be honestly one of the biggest headaches in the whole process, is figuring out the correct shape. You're going to spend the most time in retail refinement in getting that shape correct. Okay, so you're able to calculate the intensity at any given 2 theta. You know how it interacts with the different elements and the different radiation sources. You've even got the ability to fit the sort of peak shape. How do you know if you've done a good job, right? One thing is you could just look at it. Like you could look at the simulated and the experimental and say, well, it seems like it's a kind of a good fit. But how do you be more quantitative, and how do you apply a least squares regression to this? To do that, we have to go point by point and evaluate the goodness of the fit, right? And there's different tools for doing that. You will commonly see RP, RWP, and GOF, that's goodness of fit, sometimes written as chi-squared. I think the best one that you should go off is RWP or RP. And the reason why is because goodness of fit can give you an artificially good value just by having bad experimental data. If you measure really noisy experimental data, because this is a ratio of your refined fit to the experimental values, it could tell you that it's a really good fit even when it's not. So anyways, that said, there are some rules of thumb. If you're going to publish this in a journal article, right? If you want to have like high confidence in your refinement, what you're looking for is a weighted residual of something like less than 10%. You want 10% deviation or less. And the way that's calculated is it literally just goes point by point in the X-ray that you have simulated versus the actual measured values, and it just compares them. It says, what's the absolute value difference between your observed point and your calculated point, right? And then divide that by what the observed point should have been. That would be the RP. RWP is a slight variation on that, where it takes the difference and it squares it, and then it takes that whole thing to the 1/2 power. And what that does is that it penalizes you more for getting your intense peaks wrong and less for getting the low intense peaks wrongs, which is maybe a good idea, because if you think about like right over here, right? It's less important for you to get the background right, since after all, it's just background. It's more important for you to get the actual peaks right. So RWP, in my opinion, is probably the best one to use, but any of these are going to be acceptable. And you're going to try and aim for, obviously, as low as possible. You'd love to get it dialed in and perfect. But your ability to do that will be a function of both the quality of your data that you collect, as well as how accurate your model is that you're fitting to your data. And more on both of those in a moment. Okay, the process of Rietveld refinement is a bit ambiguous. In fact, there's this famous quote. It says here, a Rietveld refinement is never finished, only abandoned. So why do they say that? The reason they say that is because as you're doing a refinement, you don't know whether you have reached the best result or not. You could be, as your the y-axis represents, for example, say our RWP, and we want to make that as low as possible. Ideally, it'd be perfectly zero. In reality, it's never going to get there. But maybe you're over here on the x-axis, maybe you're changing your parameters, you're fixing the lattice parameter, you're changing the profile shape, and the values are going down, so it's minimizing the error, therefore it's looking more and more like a fit. You could actually be stuck in what's called a false minimum, and the true global minimum could be somewhere else. So how do you make sure that you don't end up there? This is one of the, I think the downfalls of felt refinement as a technique is that it's very difficult to know whether you are in a false minimum or a true global minimum. There are some things that we can do to try and do it. First off, you can try different models. You know, usually with X-ray diffraction data, you're trying to fit that experimental data to some model. Maybe you're like, I'm pretty sure my structure is some monoclinic phase, but maybe you have a hunch that it's possible that it could also be a cubic phase. So great, you could try and fit it to both and see which one gives you the lower overall error. And then you go with that one and say, the evidence supports that it's this phase as opposed to the other. But the fact that you tried both makes it so you're more confident that you didn't just get stuck in a false minimum of only trying one, right? There's also things in the software itself that can try and minimize getting stuck. For example, you can take bigger or smaller jumps along the x-axis here, which represents how much you're willing to change your parameters at a time. Changing them a lot, taking big steps, changing the values which would be changing the values a lot, is more likely to find the global minimum, but it's also more likely to do what's called diverge. And when in an ideal scenario, you would be making small changes, but you'd be continually getting lower and lower and lower until you find a minimum. Divergence happens that when you're changing things, it's not minimizing, it actually starts to increase. And that usually is indicative of your structure starting to pick completely silly values that no longer even kind of fit your data. And the software is programmed to stop running at that point and go back to the previous non-diverged value. We will probably see some examples of that when we actually try this out today of what it looks like when it diverges. Okay, so we'll come back to that. That said, be aware that it's sometimes frustrating with refill refinement because you never know if you are done, because it is never done, it is only abandoned. At some point, you just throw up your hands, you say, that's good enough. And usually it's good to know, like, what is it that you're actually looking to get out of this? Are you looking to get out of it just the lattice parameter? And if so, to what accuracy? And is that a realistic accuracy for the data that you've collected or for the structure that you're investigating? Or are you after the weight fraction of multiple different phases? Okay, if so, to what weight fraction percent accuracy are you going to be satisfied? And once you've reached that, that might be your stopping point for the refinement. Anyways, so that said, let's talk about some examples. This was my very first data. So you can see the samples are labeled TS, that's my name, Taylor Sparks, and then 021. This is the 21st sample that I investigated when I was way back in grad school 15 years ago or so. And at the time, my advisor was having me look at a three-phase mixture. I think it was a mixture of alumina, YSZ, and calcium oxide. I can't remember. And he wasn't sure if what we were going to get was going to be a three-phase mixture or if they were going to react together to form a single phase. The phase diagram at this temperature was not calculated. At least there was some uncertainty. And so he just said, try it out. I want you to go to the lab, mix these things together, fire them to the different temperatures that we were interested in, and tell me what forms. And this is the data that I collected. So you can see in this data, first off, it's got a really high background, 2,500 points, but my most intense peaks are only 4 or 5 times higher than that. So I have a really high background. I have this really big bump over here on the left at low angles. That is very characteristic of what we call amorphous. That's an amorphous bump, and it means that there's some of your material which is not crystalline. It's an amorphous mixture, and so it's doing what we call diffuse scattering. More on that in a few slides. So looking at this data, I had some clear peaks, and I had to figure out which one of these corresponded to different phases that might be possible. And I had a bunch of amorphous material. And honestly, I was pretty stumped on how to go about analyzing this type of data. I thought I saw evidence that there were some multiple different phases present. For example, I was using a software called HighScore, which does this sort of peak matching analysis, where the peaks that you saw here, it actually puts stick values to those, right? Here's those peaks, right? And then it has a database and it tries to match the peaks. So it says like, okay, this phase in red kind of looks like it accounts for some of these peaks, but not all of them. Like this big one right here is not accounted for by the red or the blue phase, but it is accounted for by this green phase. And so using this approach, you can try and figure out which phases are present using this peak matching. But then how do you know how much is there? Like it looks like green is there. Is it the majority of the peaks? Like, is it the dominant phase? Does it make up more than 50%? Is it less than? To do that, you have to actually refine the fraction of the phases present. And the most common way to calculate the weight fraction is by using the SMZ method, right? So S is going to be the phase fraction, which will be proportional to the number of unit cells measured. That's the concept anyways, that the overall fraction, phase fraction, will be proportional to the number of unit cells measured. M becomes the molecular weight. Z is the number of formula units present in a unit cell, because again, not all unit cells have one formula unit. Some, in fact, they very often don't. They have 2, 4, 8 commonly. So SMZ allows you to calculate the weight fraction by taking the SMZ values for an individual phase and dividing it by the SMZ product for all phases that are being simulated in your model, okay? And this works really well. So this is not my research. This came from a workshop I attended once back in 2010, where you can see this is from a round robin where I think NIST did this. It might have been somebody else. I'm pretty sure it was NIST, where they actually put together mixtures of alumina, fluorite, and zinc oxide in different ratios, and they mailed them out to a bunch of different participating labs. And they, without telling them what the actual fraction was, they said to them, you do the Rietveld refinement on these and report back to us with the best accuracy that you can achieve what you think the correct weight fraction is. And here what you see is, okay, what the actual result was and what the refined result was from the different approaches. And you can see that it's pretty good. People were able to pretty well and accurately calculate these values. By the way, if you want to read more about this, the paper is great, and I've got it in the notes. So if you jump over to the notes, it will take you to this paper. Where is it? It is this one, where you can actually see, here's this outcomes of the International Union of Crystallography Commission on Powder Diffraction, round robin on quantitative phase analysis. It's really great. You come down and you can see these type of plots, and you can see just how accurate they are. Like you see what bias is present in different types of samples. So if you really want to go down that road and learn about what sort of precision and accuracy you can expect from refinement, you can check these out. They're really good. But I'm going to say that it is possible to do very accurate weight fraction analysis. Now, very accurate depends on, again, how good of data you're starting with. If you're using lab x-rays, like if you guys are working in industry or if you're at a national lab or something, and you're doing just a regular benchtop or a standard X-ray diffraction system, you can expect to get weight fractions accurate down to a few weight percent, like maybe 5 weight percent. If you're reporting it less than that, I would start to become skeptical. If you collect higher quality data from, say, like a synchrotron source, then you can get it even more accurate, down to 1 weight percent or maybe even less. More on synchrotrons later. And then here's some examples of that. So back in grad school, I had a student who was actually trying to recover tellurium from a biological process. So they would expose it to bacteria and show that the bacteria could convert the tellurium in the seawater to, a different format where it would precipitate out. But to start with, he had to actually mix together some sodium chloride and tellurium. The amount that he mixed was 5% tellurium in sodium chloride water. When we dried off the water, the stuff that was left over was sodium chloride and tellurium. And when I did a refinement of it, I was able to get my weighted residual down to 6.9%. And I found, using the SMZ method, that it was 94% sodium chloride, 6% tellurium, which is very close to what the actual value was that we knew ahead of time, which was good. That gave us some competence in this process. There's, of course, some errors. We had a small volume that we were working with. We had some transparency or absorption issues where the tellurium and the sodium don't absorb X-rays at the same ratio, and so you need to correct for those. But that's, I think, what the errors were causing. Here's another one. We were looking at a series of garnets, and in this case, we were able to determine that there was actually 3 phases present. The weighted residual became very low, all the way down to 5.3%. If you take a look at the intensities, look how good this data is. Like the baseline is at, I don't know, maybe 3,000, but our most intense peaks are at like 65,000 counts. So this is really good signal to noise ratio. I think that's because we measured this over like a weekend. We did a really slow scan and collected this data as accurately as possible with the smallest step size and the narrowest optics that our instrument would allow us. And that's essentially what you want to do. If you're going to be doing repeat refinement, then it's probably worth it to really do a careful scan of your data. Because if you do just a quick and dirty scan, like those 10 or 15-minute scans to do a phase ID, then it's going to be so broad with such bad signal to noise ratio that that will really impact your ability to get a good refinement. But if you take the time and do a really careful scan, then you can get really low weighted residuals and determine quite accurately. In this case, we had 3 different phases present, and we were able to model them really nicely. Here's another example of that where we're able to do even better signal to noise ratio up to really high angles, and you can fit it. Down at the bottom, you're seeing the difference curve. So the red represents, okay, if you took the actual values and subtracted from that your simulated curve, what does it look like? So you'd like it to be 0, you'd like no difference. And it's pretty much 0. It's messing up the shape, a little bit of our big peak, but that's a really good fit. Okay. Now, I showed you previously, if you go back to that very first example I did, there's this big amorphous bump. Most of the time in diffraction for the last, gosh, a long time, we've just been ignoring that. When I do the refinement, I would actually set the start point at like 25 so that I wouldn't even try and fit this amorphous material. But it is possible to fit that amorphous material using what's called the Debye equation. So the Debye equation has it looks different than what we saw previously, and it takes into account amorphous scattering. So instead of looking at the Bragg equation where there's a very specific interplanar spacing, right, that has a very specific d spacing, and you use that d spacing to calculate intensity. This is not doing that. It's saying every different atom, they all have different spacings, and if you understand the distribution of those spacings, then you can get a distribution of conditions that satisfy the Bragg equation, and that is the Debye equation that does that. So to do this, you need a radial distribution function to determine your bond distances for analysis. I would say in the last 10 years, this has become really powerful and a really popular tool. Something that, when I first learned about this back in 2010, they were saying like, yeah, it exists, but nobody really uses it. I'm seeing this all the time in the literature now. So people are increasingly looking at actually trying to extract information from the amorphous materials using the Debye equation, okay? So let's say you take a material like this is a silica glass. So it is not crystalline at all. As you can see, when you look at the diffraction pattern, there's no sharp peaks. There's just one really big amorphous bump. What you can actually do, you can fit this to data and extract out of it this distribution function, which will tell you, that's what you're seeing here is a radial distribution function that tells you that there's a peak in distances, which these are essentially telling you where common distances are, as if you even in an amorphous structure, which is pretty slick. Here's another one, a different silica gel where they're able to fit it and find a bunch of common distances. So people are using this for all sorts of analysis in batteries, for example, and it's become a really popular area. It's not one that I know particularly well. Okay, another thing that you can do is you can extract things like atomic positions and site occupancy. So let's look at this apatite crystal. The apatite crystal structure is pretty gnarly. You've got multiple different cations. You've got these SiO4 tetrahedra shown here, and they are surrounded by these gadolinium and calcium that sit on different sites. You can have interstitials as well as vacancies. It's kind of a complicated compound. And so if you tried to investigate this complicated structure with lab X-ray, most of the time I think you're going to find that it is insufficient to do a lot of things you might care about. For example, here's some real data that I collected. No, this one's not my paper. I have a different one. But you see these little stars from this paper. This is very common literature where some of these peaks are labeled, like that's the 102 peak, that's the 210 peak from this, apatite phase. But then they've got these little tiny stars right here and a few other ones over there. These ones don't match the apatite phase, and they have them labeled. They said, oh, this is actually gadolinium silicate. It's an impurity phase. And in this case, it would be very hard to make a determination of how much of that impurity phase is present because it's just a tiny little peak that you'd be trying to fit it to. So that could be 5% impurity. It could maybe even be 10% impurity. The point is that you don't really know using lab X-ray. It's just too small of a peak to try and fit. You know it's there, but I would be very hesitant to state how much is there. Um, there can be volume changes, like in this case, as they change the X value, which is going to change the ratio of your gadolinium to your calcium, that will change vacancies, that will change the overall size of this. So if you look closely at this, as they go from X equals -2 all the way down to X equals +2, you would expect that there'd be a volume change. So that would show up as the peak distance or the peak position slightly changing. So maybe you could extract that, maybe. Um, is there a cation site preference? So there's different sites where these different cations can occupy. Let me pull it up really quickly so you can see what those look like. So in the apatite structure, they typically call it the A1 and the A2 site. Actually, this is from my paper, this blue and orange figure. So you can see that like the A1 site is shown as the orange values here, and then you've got your A2 site shown in blue. The point is that these can actually switch sites. You can get some occupancy of the orange atoms, maybe that's your gadolinium, occupying the blue site, which is your calcium, and vice versa. So that's something that you should be able to extract from Rietveld refinement. But using lab X-ray, it might be difficult to get enough accuracy to do that. And then finally, small changes in the actual positions of these tetrahedra manifests itself as what they call this metaprism twist angle. I guess I'm pointing out that all these things that's probably, you might be interested in many of these things. If you're interested in, say, battery research or ionic conductivity or whatever else, very often those slight changes to the crystal structure, that crystal chemistry is responsible for the improved properties. And so you'd love to investigate those things and tie them to your observations, but doing so might require better accuracy than a lab X-ray can provide, which is why very often you might be turning to synchrotron as a source. Now, there's some real benefits to that. Synchrotron diffraction will give you extremely good signal to noise ratio. The intensities can be several orders of magnitude higher than what your lab instrument can do. They have also extremely good optics so that the resolution is very, very good. Instead of getting these really broad peaks that might take up 1, 2, 3 degrees in 2 theta, these things can be really sharp. And they also can pick the exact wavelength because it's a tunable electron beam that creates the radiation source. You can get the exact wavelength to minimize anomalous scattering. Whereas if you're using your diffractometer at your lab, you've probably got like a copper source, a molybdenum source, chromium. First off, swapping the source is not like the easiest thing to do. And you've only got a couple to pick from. But with a synchrotron, it's a continuous range of values that you can choose from. So here's what you can expect to see. Here's an example of that same apatite problem where we sent it to a synchrotron to collect it. Take a look now. Our background is effectively 0. It is a very low background. And the intensities, these are 6 times 10 to the 4th. So extremely high intensities, extremely low background. And the sharpness of these peaks, I should have actually zoomed in on it, but they are crazy sharp. So that we were able to actually now refine this phase. And we found that okay, the weighted residual got clear down to 6.29, so that's a very good fit. You see that the difference curve is effectively 0 everywhere. We have 2 phases present. We have the apatite phase, and we had a little bit of that gadolinium silicate. We can now say with confidence exactly how much of that impurity phase is. There's 14%. It might have only looked like a little blip on your lab X-ray, right? You might have been tempted to say, oh, there's probably basically nothing there. But when you actually do a more careful measurement, you find, well, shoot, there was 14% there, which changes your overall chemistry, right? My initial composition was 8.33 to 1.5 calcium. But you see that some of the gadolinium and none of the calcium was taken up by this phase, which changed my overall ratio. which is something that you can now refine for. Furthermore, we saw that there is about 5% of the calcium is occupying this A1 site. So there's some cation site inner occupancy. And we were able to very accurately measure this metaprism twist angle. So I don't know what problems you guys will be interested in, but I'm guessing that some of the same sort of analysis might be useful. And so it's going to be very useful for you to at least know that synchrotrons are available as an option. And actually, they're a pretty available option. So the best one that you should be aware of is the 11BM synchrotron. If you guys are companies in the United States, then you have access to this. You know, if you're a US citizen, your tax dollars pay for this. And what's great about the 11BM is that looks like it's down right now. It'll be up again in the fall, but it has this amazing mail-in system, which I have used before. What's great is you have to write a proposal to get it. It's only like, you know, it's a short proposal to go for this. You can learn about it on this website, but you can apply for beam time. And if you write a brief but compelling proposal, and odds of winning it are actually pretty good, then they will award you beam time where they will send you the little samples. Maybe it'll show some pictures of it here in their mail-in. No, they don't. But they mail you little sample holders. You put your samples inside these tiny little Kapton tubes. You package it with a little QR code on the bottom. You mail it back to them, and they do the experiment for you so that you don't have to travel and do that or do the safety training or worry about security issues or anything else. They just do it for you, and then they mail you the data back. They email it to you, and it is extremely high quality data. So in my slides here that you're seeing, all of these were done with that mail-in service. So I didn't have to go to the national lab. I was able to write a brief proposal and get this. And if this is something you want to do, then we can talk more about what makes a strong, compelling proposal and what isn't. And the beamline scientist, you just saw his picture there a moment ago, Saul Lapidus, is a great guy. Very, very anxious to grow his user base and get people, especially from industry or non-traditional, you know, users of the facility to start using it. After all, it's supported by our tax dollars. So, and it can make these incredibly powerful, you know, measurements, which then allow us to do much better refinements. Okay, something else that we can get from Rietveld refinement is thermal displacement parameters. You're all likely aware that atoms are not static. They don't just sit in place. They're vibrating all the time. And in fact, we can quantify how much they're vibrating, like how big is that distance that they are vibrating. You can do that assuming that they vibrate in a spherical, like that they vibrate in all directions. That's not realistic, but it's an easier one to model. Or technically, you can model what the anisotropic vibration, like maybe it's an ellipsoid, right? And it's a very specific way that it's vibrating. It's vibrating in the X and Y direction, but not in the X and Z direction, right? This is all stuff that you can get out of Rietveld refinement. That said, if you want to get anisotropic vibration, like the non-spherical approximation, you're going to need synchrotron data, maybe even need single crystal and synchrotron data. If you're trying to get that data from powder diffraction, I don't think you're going to be successful. From powder diffraction, you can get U ISO values, which is an assumption of what the spherical value would be. And maybe that's useful. Like here, for example, this was from research I did back when I was a PhD student, but you've got a bunch of different rare earth strontium aluminate compounds. And what we found is that the thermal conductivity of these things, there was a trend where lanthanum had like the highest thermal conductivity, and then they went down to lower thermal conductivity. And we were curious if there was essentially like a rattling of ions, and the rattling was causing a reduction in the thermal conductivity, which is a pretty well-known mechanism in other compounds, but we've never observed it in this one. So to investigate that, we set out to see, do we see larger values of our thermal displacement parameter? And by doing the refinement, we were able to extract that value. Like take a look here. As you go in the first column, lanthanum, all the way to the last column, dysprosium, we see two things, like the occupancies change. They basically switch, like where is the rare earth sitting? Is it on the A1 site or the A2 site, which is either in the perovskite slab or the rock salt slab? That changes. And the thermal displacement of the A1 site, this guy here in the middle of the perovskite layer, increases from 0.11 to 0.96. So it's a dramatic increase in the vibration. So this seems pretty compelling that what's actually happening here is probably a thermal displacement causing the reduction in thermal conductivity. Okay, another thing that you can get out of Rietveld refinement is preferred orientation. Here's another paper from grad school where we were able to make powder strontium niobate. And in a powder, if you've crushed it and it's not, you haven't oriented in any specific way during loading your sample, then you would expect to see this random orientation where all different diffraction peaks have equal chance of seeing the incoming laser and diffracting. But if it's a textured sample where those things have been lined up, like maybe you pressed on it over and over, which is what we did here. We did what's called sinter forging. When we sintered it, all these ceramics were able to lay down. It was able to texture them. So imagine if you had a bunch of dinner plates, right? If you sort of stack them helter-skelter, there'll still be like some net sort of orientation. And that's essentially what happened in this sinter forging process. So we were only seeing diffraction from the 0B0 planes for the most part, as opposed to the random where you saw all those. And you can actually account for this in the refinement process. Here we were able to introduce texturing, get the weighted residual quite low, and show that it has a texture index of 5.52. What I don't know is how that actually relates to things like Laudring factors, which are more common measurements, but at least you can account for it so that you could figure out, say, lattice parameters or weight fractions doing this. Then the last thing I'll talk about is that you can also get things like size and strain out of your refinements. To do this, you first need to very accurately know what is the broadening in your sample due to the instrument, okay? So when you measure something, the peaks are not perfectly sharp. There's some broadening in the shape. If you know what amount of that broadening comes from the instrument versus the sample itself, then you'll be able to calculate size and strain effects. And the math is sort of shown here, where essentially you say that if you compare the observed versus the instrument values for the broadening, there's a linear equation where the coefficients are equal to the slope and the intercept are going to give you your size and strain. To do that, you're going to have to accurately determine how much comes from the instrument. And I'll show you how to do that in our first example. But here's just an example of what it looks like. So here you're seeing cerium oxide before and after micronizing. So the micronizing is doing something to strain the material. I assume it's like a ball milling process or something like that. On the left, you see really sharp peaks, right? These are crazy sharp. And on the right, they're significantly broadened. They're in the same position, but they're broader. So you can actually do a refinement on this and figure out what is the width of these peaks and use that to extract out the size and strain. In this case, they were able to determine that the size of these damaged materials is now grown to 226 angstroms. Sorry, it's shrunk. They've damaged it, so they've broken particles down. Smaller sizes particles give you broader peaks. So these are nanoscale, basically, like 26 nanometer peaks. That's pretty small. They're small crystallites, and they have quite a bit of strain, 0.011% during the deformation process. Okay, wrapping up, before we now switch gears and do some examples, I'll say that ReefFell refinement is an awesome tool. It allows you to quantitatively extract information from your X-ray pattern. I'm guessing many people on this call have done X-ray before, and I'm guessing that probably what you've done is determine which phase is present, maybe it's lattice parameter, and maybe you've tried your hand at doing quantitative. But using ReefFell refinement, you can accurately do all of those things and much more. You can extract crystal structure information, things like positions, displacement parameters, occupancies, and you can get other information like size, strain, preferred orientation, and a lot more. So with that said, you have access to those slides. Feel free to refer to them, and we might jump back to them ourselves. But what we're going to do now is actually do some examples from our wiki here, or this GitHub page, I mean. So if you want to follow along with me, we're going to go to the examples. And the first thing we're going to do is we're going to do this Lab 6 example. And I'll show you why. Lab 6 is a well-known X-ray calibration. Lab 6, XRD standard. So you can buy this from lots of different people. So right here, for example, Sigma Aldrich is selling this powder diffraction NIST SRM 660C lanthanum hexaboride. So the fact that it says NIST SRM 66C, that means that this comes from a protocol developed by our National Institute of Standards and Technology, which is the right people to do this. It's a very specific way of making this lanthanum hexaboride such that you know exactly how big it should be, what the exact lattice parameter should be, and you pay quite a bit for it. To buy this standard, you only get 6 grams of it, and it's $1,600, so quite expensive. There's other standards out there, but they're all going to be kind of similarly expensive. The benefit, though, is if you go to this and you actually look at the diffraction for it, here's what you see. You see very, very sharp peaks, right? This is, yeah, it says Rietveld refinement of lanthanum hexaboride. Assuming that this is some standard, you get really carefully controlled peaks, and therefore you can fit your model to that from your instrument. And this should be able to tell us the broadening that comes from your instrument versus your samples later on. It's also able to tell us what the zero and displacement error is on our instrument. Okay, so let's jump ahead and go do that. So I'm gonna hop over to my main screen. I'm gonna open up GSAS2. So if you've had a chance to download this and you'd like to follow along, please do so. If you'd rather just watch, that's fine too. Like I said, this is all being recorded, so you'll be able to come back to it later. And if you have a question when you try to do it later on, you can always reach out to me, and it's not a big deal. What's great about GSAS, sometimes called PyGSAS, is that it runs on Python. So you probably already have Python on your computer if you're doing any sort of scientific computing. If not, it's not too bad to download it. And when you do so, you'll get this. You'll get to this screen. So what's going on here is I've got this. Right now it lands in this one where it's got the file, data, calculate, import. This is what I'm going to call the data tree, and I'll show you that in a moment. And then it will have another one, which will be your plots. I'm going to minimize this for right now. We'll do our plots in a moment. So over here, GSAS2 plots and our GSAS2 project, okay? When you do the process of Rietveld refinement, the first thing you have to do is have data, right? You had to go to the lab and you had to collect some data. In this case, I've done it for you. I'm going to go back to my here. What I have here is on my computer, I have the same folders that were present in this GitHub repository. So if you downloaded the same files, if you came over to code and you downloaded this zip, then you would have the exact same files that I have right here. Here you've got my slides that I just went through. And then if you go up on here in this examples folder, here's the 4 different examples that we're going to go through over today and tomorrow. We're going to start today with this lanthanum boride one. And inside this lanthanum boride, there is a what's called a .civ file, which if you open this up and you look at it, you're going to see that, oh, okay, this has information about the lanthanum hexaboride phase itself. It tells you that it's a cubic crystal, that it has that space group. In international terms, it gives you that. Here's the angles, it's cubic, so we knew those would be 90. It tells you what the lattice parameter is, and this is known very exactly because this is a standard material that comes from NIST. We know very accurately. In fact, 4.157597, maybe we can actually look up what the NIST standard is. So NIST SRM 660C, and let's see if we can find this from the actual NIST website. So here it is. Here's the certification standard reference material for the 660C, and it tells you exactly what the lattice parameter is. So it's lanthanum hexaboride. Here it says, okay, right there, it said, if you do your measurement at 22.5 degrees Celsius, so basically room temperature, then the lattice parameter is 0.415682.6 plus or minus that tiny value. They have 95% confidence in that. That's why you pay $1,600 for 6 grams of this stuff, is because you know this value. This value is what you need. Because see how different it is, right? This one right here, 0.415682. Let's look at our sieve card. 0.415759. It starts to deviate significantly more than what this value is. Now, I don't know if who made this or where the sieve card came from, but if this is the material that you bought, then you're going to change this value so that it is this one right here. Sorry, you're going to change this value in this sieve card, and you're going to replace it with the actual value of the stuff you paid for, right? Because that's what you're paying for, is to know exactly what this lattice parameter is. But the sieve card tells you all this other stuff. It tells you where the atoms are located, what is their thermal displacement values, right? Here's that U iso, that's our isotropic thermal displacement. It tells you what that should be. Will tell you occupancies. In this case, these are both fully occupied, 1.0. And it tells you where they're located in the lattice, right? At the 0, 0, 0 position, at the 0.5, 0.5, 0.2021 position. And again, anytime they show you this 0.2021 followed by something in parentheses, that's the uncertainty. They have some uncertainty in where it's located in the thousandth place, right? Okay, but that is this sieve card that we are going to use. That's one of the things that's present here. The other thing that's present in this folder, this one, my computer thinks it's an image because it's a .raw file, and that is usually an image file. In this case, it is not an image file. It is a raw file, which is a way of formatting X-ray data that Bruker uses. And I wish they didn't use raw because it confuses your computer, right? If I try and double click this, my computer's going to be like, hey, I don't know how to open this, and it's not going to work. It's giving me all this image tools, but it's not working because that's not an image file. It's a data file of X-ray data. Okay, but the point is, for this example, we have data, and I have what's called a structure file, a sieve file. Okay, so we're going to use those. So let's come back over to our data tree. The first thing I'm going to do, and by the way, the steps that I'm following can all be found right here under slides if you go to steps. So before you do your refinement, this is like making sure that you have the data. And then when it comes to actually what the steps I'm going to do right now, they can all be found right here. We're going to open a new project, save it to a name, import the data. You can follow along as you like. But yeah, the first thing let's do is let's name this thing. So I'm going to save a new project. Let's save this as, I'm going to work on lanthanum hexaboride. So I'm going to do it in this folder. In fact, I'm going to make a subfolder where I actually do the refinement and do it in there just so it's clean. So I'm going to call this test. You can name it whatever you want. I'm just going to call it test for right now. So now I have a project called test in that exact folder. Okay. So next thing it said is, okay, you need to import the actual powder diffraction data. Great. So to do that, we're going to go to import, and there's lots of things that you can import, but we want the powder data. And check it out. There's all these different formats that their GSAS software knows how to bring in. So we know that this is a Bruker raw file. So I'm going to select that first one, Bruker raw file, and it's in the refinement folder. So I have to step up one, and there it is. There's my raw file. So I'm going to say, yep, that's the one. It says, is this the file you want? Do you want to read this file? Yep, that's the one. Okay, now immediately it opens up. You might look at this and be like, oh, did that not work? Because it's like it's asking me the same question, but it's not. Now it's saying choose the instrument parameter file for lanthanum hexaboride. We don't have that yet, and I'll describe what that is. The instrument parameter file, it describes the optics of your instrument, right? All these different X-ray diffractometers that are out there. Let me show you a picture of these. Different machines will have different tools that they use. Like here's an example of one, right? Like the slits that you use, the distance from the X-ray tube to your sample, the distance from your sample to the measurement machine, all of these they can be different for different tools. Like the goniometer angle and that are going to be different. So ideally, you need to figure out an instrument parameter for every different instrument because they'll all be a little bit different. And so that's what it's asking for. It's saying, okay, tell me what instrument parameter file to use. So I haven't provided you an instrument parameter file yet. So we do that on purpose. I'm going to show you how to do it both ways, both using one if you have one, or if you don't have one, what do you do? So I'm just going to hit cancel because I don't have one. And it will immediately say, okay, then select the default instrument parameters that you should use. So I measured this using a copper K alpha lab data, and it's going to pick some generic values that fits most copper-based lab systems. That's fine for now. If you knew what your exact one was, you could pick one of the exact ones that it had available. But as soon as I loaded it, take a look now, so I'll close these other things. Now my plot actually shows the actual X-ray diffraction pattern, right? Over here, I can see, I'll make this a little more space. I can see that it has diffractions at about 21 degrees. If I actually hover over this, let me make this a little bigger, right there. So on the bottom down here, just below everything else, you see the 2 theta equals. If I hover over a certain spot, it now tells me that I've got at the 2 theta position is 21.349 degrees. If you want to be more accurate, you can click this little magnifying glass button, and you can actually zoom in on a peak and zoom in again as many times as you want, and then hover it right over that. And now I can read that the peak location for me, it looks like it's at 21.374, right? So you can actually read out pretty carefully what the 2 theta value or the D value or what the Q value is. More on that probably tomorrow when we talk, or maybe in 2 days when we talk about plotting. We'll talk about should you plot it in 2 theta, D, or Q space. I've got some opinions there. But this is a cool way to sort of visualize your data, and you can zoom in on whatever portions of this to see. You'll notice that these are very sharp peaks. In fact, you can see right here on this one, you can see there's the main peak and then there's the secondary peak. That's because most lab diffractometers, which is what we measured this on, they don't have pure radiation. Some of you might be aware, but you typically have copper K alpha 1 and 2 wavelengths. So if you look at the way that we generate X-rays right here, when we knock out the way that they generate X-rays is you take a material like copper and you knock out an inner electron, and then the outer electrons from like the next level up will fall in. But the point is that even though, let's say you've got 1, 2, 3, 4, 5 of these levels on the L shell, they're not the exact same energy level. They're slightly different, just a little bit. So this electron falling down is not exactly the same as that one falling down. They're slightly different. So they're both K alpha, but 1 and 2 means that they're slightly different energies. And so you can actually see that they're slightly different. Like here's what a typical X-ray emission spectra looks like. You have this broadband emission, that's your bremsstrahlung radiation when you bombard it. That's things bending basically. But then you have very sharp emissions from your K alpha, and there's actually 2 peaks here. If you zoom in really close, there's 2 different ones very close to one another. And then you've got K beta. If you are familiar with using X-ray diffraction, you know that you typically insert something to absorb K beta. You don't want it poisoning your data by getting something really far off. But it's very, very difficult to separate K alpha 1 from K alpha 2. Those ones are going to be very, very close together. Yeah, like take a look at here. Here it's showing, it's putting numbers to it. The difference between K alpha 1 and K alpha 2, here's the wave numbers, 933 and 952 electron volts. Like that is very small difference in energy. It is a noticeable actual difference. Like they have different quantum numbers, but they're so close together that they are very hard to separate. And what that means is that instead of having a single wavelength coming in to satisfy Bragg's law, right? Bragg's law is this basic one that says, right, let's show which one, let's show this one. It says, right, if you have, what's that? Right here. Bragg's law says incoming radiation wave, right? It's going to travel an extra distance based off of this D spacing, and it will have it'll either satisfy Bragg's law or not based off of that D spacing. The problem is that if you have K alpha 1 and K alpha 2, you have 2 different solutions. So the same D spacing will have 2 different solutions of positions. And we can see that in our data. Like, look at it. Like if I zoom in on this one, especially at high angles, this is 1 D spacing, but that's K alpha 1 and that's K alpha 2. You don't have this problem if you use synchrotron data, because synchrotron data doesn't use the same approach for generating data. So it can have just a single peak. You don't get the double peak coming from K alpha 1 and K alpha 2. But most of us don't have access to a synchrotron, at least not all the time. So we are stuck with this, where again, if you zoom in, not very much, you don't see it, but if you zoom in closer and closer, you'll see that these actually are 2 different peaks. At low angles, the separation is very small. So here's one at 20. Can we even see it here? Not really. That looks like a single peak. But as you go out to higher and higher angles, especially these ones at really high angles, it becomes very pronounced that there are 2 different peaks there. And again, that's because you've got technically 2 different sources of radiation coming in. So that's slick that we can actually see that. We're able to visualize our data using this plotting software. We now have a bunch of new stuff here. Before, this stuff was all white, but once you import your first import your first pattern, now you have lots of stuff, right? You can look at, say, like the background. You can look at the instrument parameters. Again, because we didn't know what instrument parameter to use, it's using default values. Like that the ratio of K alpha 1 and K alpha 2 is 0.5. That's typical. You'll just leave that alone. It's assuming that there's no zero problem on the instrument, but in actuality, X-ray diffractometers do have zero problems. So a zero error is one where the angles are not quite aligned the way that you think they are. Let me find a good image that shows this. Well, we can use this first one. So the whole process depends on you having an assumption about the exact angle. But if this machine, you think that it's at 45 degrees and it's actually at like 44 degrees or 46 degrees, that means that your zero is off. Right now, by default, it's saying that it has no zero. But we are going to learn what the actual zero is and then use that going forward. This is why you always, before you do refault refinement, you always pay the money to have that standard, and then you can keep on reusing the standard. It's not like you have to dispose it, but you measure it on your machine to determine what the zero is, because as those goniometer arms move up and down, they will be slipping over time. And so we here at the University of Utah, we run this typically once a month or so. We put the standard on there and figure out what is the zero, and we see, is it changing? Is it shifting? And that actually can be a pretty good diagnostic tool to tell you whether you need to change your instrument and fix that or not. But it also has these U, V, and Ws. If you remember, those tell you the shape of the peak that gets generated. And then X and Y, these are also for shape, but they give you Lorentzian. The UVW give you Gaussian shapes. The X and Y give you Lorentzian. And then there's this SHL, which gives you asymmetry. More on all this in a moment. So going back to our things that we need to do, we've been able to import data. We were able to look at it. It looks good. So now we need to actually, so here it's telling me to switch things over here to make sure that all this stuff actually accurately represents what you've done. So you can look at your sample parameters, make sure that the diffractometer is correct, whether it's Bragg-Brentano or Debye-Scherr. This can be Bragg-Brentano. If you know what the goniometer radius of your instrument is, you can insert that. Like the default value is 250 millimeters. But again, if you knew what your actual instrument was, you could measure this distance. It'll just be known for your material, like a Bruker D8 goniometer distance. You could just probably look it up. Like if you have a D8 Discover, then it's a 200 millimeter goniometer distance. So you could update that value. Like that's one of the tools we have here at the University of Utah. So I would come over here and I would replace that with 200 if I knew that that was what my instrument was. For this data that I'm using today, I actually don't remember what instrument we measured it on. So I'm just going to leave that alone. It doesn't make a big difference. But this has a bunch of other info we'll get to in a bit. Things like, do you know that there's going to be a displacement problem? Was your sample too high or too low? Then you could input that. Like maybe for some reason you know that it's actually 10 microns too high. You could put that, or it's 10 microns too low. You could put that. For here, we're just going to leave it because we don't know any of that right now. So the next thing we do now that we've got data in is we need to go ahead and find a structure that we're going to try and fit to that pattern. So the structure that we're going to import, we're going to import a phase. And which ones of these are we going to use? Well, we go back to our folder, and what did we have? Under my examples folder, in the lab 6 folder, there was a CIV file. That stands for crystallographic information file. So I'm going to come over here, and when we import phase, I'm going to look for CIV, and there's a whole bunch of options. Here's the CIV. One thing you can do, by the way, is GSAS. You can import it from another GSAS refinement. So if you just finished a refinement, you can actually take that final structure that it saved and import that to your next structure. We'll show you why that's relevant in a moment. But for now, we're just going to do CIV card, and we're going to point to this one. There it is. That's our CIV card. It's going to say, okay, that's what I'm seeing. Here's the first line. Does that look like right? Looks good to me. You can name that phase. Here it's B6LA. You could write that LAB6 if that's more normal to you, whatever you want. It's just a name for it. But this is important. It says, okay, which histograms should be associated with this? And right now we only have one histogram. Histogram just means diffraction data. We only have one diffraction data and we want to associate it with it. The cool thing about Rietveld refinement is you can actually refine a single structure to 4 or 5 different measurements, right? If, for example, you use the same powder and you did neutron diffraction and you did synchrotron diffraction and you did lab diffraction and you did time of flight diffraction, right? you can take that exact same structure and fit it to all 4 different data sets. You would just have 4 different diffraction histograms, right? Here we only have 1, so it makes it easy. We just click the box for 1. Okay, so now in this, what I'm going to call the data tree on the left over here, we have one thing which accounts for the actual data that we collected. We have now a new one over here, which is our phases. And there we see information about the lanthanum hexaboride phase. Like if you look over here, here's the unit cell. Here's like the atomic weight of that. It gives you some basic data. If you click the tab for atoms, here's information about where the different atoms exist, right? It's saying that the lanthanum is on the 000 site. Boron is on the 0.5, 0.5, 0.2021. It's got these values for its U isos. It pulled all of that data from the sieve card and it populated it into this data tree, okay? Now, what's the first thing, hopefully, that you've noticed about this is this value, 4.1576, does not match what we paid good money for, right? You paid a lot of money to NIST to buy something where this is the exact value. So let's go ahead and update this value. Let's take these things right here. And I'm going to take that and I'm going to drop it in here because we know that's what the actual value is. It can't have spaces, so it's upset about that. Okay, so I have manually changed that value. Let me try that again. That didn't work. 0.415682. 0.415682. Why did it not let me do that? 0.41568. Okay. Sure that worked. That is not working. So maybe what we need to do is, that's unusual. I thought you could change that. Maybe we needed to change that manually in the sieve card. So let's
Could
remove
it be in angstroms instead of nanometers?
Ooh,
Or
that is a good catch. What was it before though? Was it
It was 4.15.
Thank you. Good catch. That surprised me. I forgot people were on the call. I'm talking to myself. 4.15. Thank you. Good catch. So that's probably like a built-in safety rail. If you put in something that's crazy too small, it's saying it can't be less than 1. So 4.15682. And let's see if that fixed it. I think that did. Okay, good. Yeah, thank you. Good catch on that. But we are manually going to change that. Normally, when you do these X-ray refinements, you're going to refine the unit cell, meaning I want you to tell me what the actual unit cell is. But for this very first one, where we are looking at a standard, we're doing the opposite. We are saying, I know for a fact that this value is 4.15682 because I paid good money for it. Therefore, if it doesn't match, it must be due to something with the instrument. And what we're actually going to be doing is refining the 0 value, okay? So we technically, we could do our refinement now, except that nothing is turned on to refine. Like all these boxes that say like, do you want to refine the 0? I haven't checked any of those boxes yet. In fact, by default, the only thing that comes checked is the background function. So let's do it. Let's do a refinement where the only thing that we're going to use is a background function, right? You can see that the background is kind of sloping and then it flattens out. And so we are going to update this. Right now, there's different functions you can use. The Chebyshev polynomial is the most commonly used one, but you could try any of these. Honestly, it doesn't matter which one you use as long as it fits. There are a different number of coefficients. You can go crazy. You can give it 36 coefficients in the background. In general, you should not be giving it many coefficients, though. It would be better to fit it to the actual data than just add squiggles to your background until it fits it. Because if you give it too many, it will start to try and fit these peaks as background, which is not the case. So let's go ahead and run it. Before I hit run, I'm gonna go up here to controls, and this is the refinement controls. We don't have to change the refinement type. We're going to do analytic Hessian. That's okay. That's the default value. These things are telling it how big of steps to take. We're going to leave all this stuff standard, except instead of doing 3 cycles, I usually bump that up to 10. 10, right? And then you come up here to calculate, and Control R will do our first refinement. So we're off to our races. We're doing our very first Rietveld refinement here. It happened really fast because there was basically no parameters. We only had 3 parameters, so it was able to run really, really quickly. And you see that it says, okay, my final chi-squared was 155. If you remember from our notes, we'd love our chi-squared to get much lower than that. And so it's asking, do you want to load the new results? Yeah, we do. So it's going to take, after the refinement, it's going to take what those new values are and it's going to fit them. And now, because we've done a refinement, check it out. Our plot looks different. We have new information here. Now we have a green line and a light blue line along with our blue plus marks. Before we only had the blue plus marks, but now check it out. Now we have the green, which represents our calculated pattern. The plus signs are our actual data, and the light blue is the difference, and the red is our background. So zooming out, the red is not exactly right? Because it should have bent right here and then gone flat, but it doesn't. So we could try and fix that. We could come over here to instrument and we could give it more background. If we go to background, we could give it more background coefficients. Like we could add it up to like 6 and see what happens. I'm going to show you a better way to do it, but we could try it this way first. So it's running. It got a little bit better. If you ever want to see those results happen really fast, if you want to go back and look at them, you can click this notebook and you can see, look, our weighted residual went from a 21% and now it's down to 16%. That makes sense. We gave it more parameters to change, so it was able to do a better job. And you can see that when I look at my data over here, look, the background, which was not fitting it as good before, it's doing a better job of fitting it, right? It's doing a little bit better here now. So the error is primarily coming, I usually look at my most intense peak and you zoom in on it and you see where the error is coming from. It's actually pretty good, but it's a slight peak shape problem. Like it's a little bit, you see how there's a little bit of a gap here that's not being captured. And it's not quite as bad on this side. That's very common. That's an asymmetry problem. Very, very common at low angles. Let's look at our lowest angle peak. We'll see it more pronounced there. Again, if you zoom in on this, most of the error is, it's always a little bit strong over here. That's very characteristic. It comes from the optics of your X-ray instrument, but it's overestimating, right? The predicted value here is too high, and usually when it's too high there, it's too low at your high angles. Yeah, check it out. See here, the predicted value is too low. So too low, and then over here, too high. That is almost always a dead giveaway that you have a thermal displacement problem. Another way to look at this is to just zoom in on the error bar and see that it switches from negative errors to positive errors as a function of 2 theta. It can go the other way. It can go from positive to negative. But when there's a systematic shift like that, that usually is telling me that my thermal displacement parameters are wrong. I wonder if this tells us the thermal displacement parameters. That would be great if it did. Can I download this? Maybe I can. I don't know if it can. Anyways, when you buy this stuff, it will come with a little piece of paper that has this information. It'd be awesome if it told us what thermal displacement parameters to use, but that's what refelt refinement's for. You could also refine them. In this case, because it's a standard material, you would want to know those, but we can also just try and refine it. So I'm going to come over here. And normally you would mess with the instrument shape, but the instrument shape is actually kind of okay. So that's why I'm going to jump and I'm going to skip it for right now. And I'm going to go to my atoms and I'm going to refine these U ISO values. Okay. To do that, you go to the refine box. And when you click this, you have to click it a couple times. You have all these options. X means you're refining the positions. XU means you're refining the positions and the thermal displacement. U means displacement only. That's what we want. But other options, F means the occupancy. Fx is occupancy and position. Fxu is occupancy, position, and displacement. Here we just want displacement for a moment. We're going to leave everything else the same. So I'm going to rerun this one more time, and let's see how it does. So presumably it went down a little bit. It went so fast that I'm going to have to go back to my notebook and look. It went from 16% fit down to 14. So it got a little bit better. And I'll bet if we look at it, yeah, it's a little better. Like this one is still overshooting a little bit. But if we look at our high angle ones, which were way undershooting, they're actually at the appropriate height now. So we fixed that problem. So we're getting closer. What else could be wrong? Well, next, let's see if the positions are correct. So I'm going to zoom way in on this and see if it's in the right position. So it looks like it's pretty much centered in the right spot. And when I zoom out and look at the high angle ones, let's ask if they are also in the same spot. They're shifted a little bit to the left, just a tiny bit. So because we would normally fix this by turning on the lattice parameter, but in this case, we know that the lattice parameter is correct. that means that any shift must be due to the instrument. So we're actually going to turn on our 0 here and allow it to shift. And it's going to make it just a tiny bit better. It's not going to change very much because it's pretty close as it is, but it should get a little bit better. So it finished the refinement. Give it a second. Let's open up the notebook, and it went from 14 now down to 13. So it got a little bit better. And now, more importantly for us, we've learned what the appropriate value for the 0 is on our instrument. It technically has a very slight error on the 0. If you're using an old X-ray diffractometer or one that's been abused or broken, if the motor has had some issue, that can be a significant value, and that might be an indicator that it's time to fix your machine. If the 0 is a large value, and I don't know how to define large for you, but certainly if it's more than a degree, like it's time to repair or replace that unit, because you're just getting, you can't trust where it's putting your peaks, right? When it says that this thing's located at 67.5, it could be off by significant values. But the benefit here is that if it's small, all instruments have some 0 problem, we can actually refine those. Even synchrotrons, right? The synchrotrons, they will run a standard on their synchrotron. And when they send you their data, they'll say, by the way, here's the instrument parameter file for 11BM. Let's actually show what that would look like. Instrument parameter file 11BM APS. See if I can find one. Standards data. Yeah, so here they go. So check it out. They're doing the same thing. They're 660C. I don't see, but they've got other samples, right? Here they're doing, oh yeah, here's 660A. Here they're doing silicon. Silicon's another common standard. Corundum, aluminum oxide's a common one, zinc oxide. So they actually run on all those, and they're reporting the values for them. And I'll bet they even show us the instrument parameter files for them. See if I can find them. Right here. Yeah, here's a instrument parameter file that you can use for using GSAS. Inside of here, it's going to have information related to, oh, page not found. Looks like I need to tell them that's broken, a busted link. Anyways, but you can download that information. Or like we're doing now, you can generate this information. Because I have a standard and I'm doing the refinement, I can learn what these values should be. So the next thing that we can do, if we want to make our pattern fit a little bit better, we can start to turn on the shape. This is where you get things, the biggest improvements, but the biggest opportunity for it to go off the rails as well. We've only got 5 minutes left, so we'll try this a little bit. So you don't want to turn on like all these things at once. Even though you might end up trying them all, you wouldn't want to turn them all at once because they're correlated features. And when you do a refinement with correlated features, they're both related, right? And that correlation means that it can diverge pretty rapidly. So we're just going to turn on one. We're going to go to calculate, and we're going to hit this refine button. Presumably the shapes have gotten a little better. I think before we see big improvements, we're going to have to fix the asymmetry problem. So if I look at this guy and we're really zooming in, trying to figure out, is the shape correct? There's still a systematic error here. Like if I go back, see how the error is primarily positive and then it switches to primarily negative? That's because there's this hump on the left, this asymmetry problem, and there's no amount of fixing a symmetric peak shape that is going to fix that. We have to deal with the asymmetry. So I'm going to turn on asymmetry right here. That's this SH/L, and that will allow us to start to capture this asymmetry problem. And I'm going to run it again. We should see significant improvement here, maybe down to 10% by the time we're done. Oh, even lower, 8% I think I saw. Let's check our notebook. Yeah, so again, here's our timeline. We started at 21%. It went to 16, 14, 12. Now we're down to 8, which again, our rule of thumb is that this is probably like publication quality at this point. Like it's a pretty good fit. And if we zoom out, we'll be able to see that like it is mostly fitting this quite accurately. By the way, look at, this must have been really good data because it's got 140,000 counts and the background is at 2000. That's a really good signal to noise ratio, whatever this data is, wherever it came from. It's pretty good. Let's now look at where the data error is coming from. So it's going slightly it's going too high. So we're getting negative error because it's going too high. Let's look out over here. Kind of similar. It's really pretty close. It's pretty good here. So what do we have left that we can tune, right? What are our different fitting parameters? If you look at our instrument parameter files, we could try some our shape a little bit more. The next most common one is to do W. We can try doing that one. I'm going to do these one at a time is the rule of thumb. You don't want to turn them on all at once. You do them one at a time. In fact, sometimes you would even, if you turn on W, turn off the U if you don't, if you want to make sure it doesn't diverge. You're trying to get a little bit better. I think probably though, the next thing we need to do, if we come to our phase, what is known about this is the lattice parameter, but they didn't tell us the atomic positions. Maybe they did on that website. Let's check and see if that card had it. If our, did it say the exact? So when you buy it, it should tell you the exact atomic position, but because they don't, I'm going to try and refine it. By the way, it's giving us red values here. Red means negative. What does a negative thermal displacement mean? It means that it's a non-physical value. It will still use it because it gives you a better fit, but it's a non-physical value. So that's a warning sign that you've done something wrong here. So usually I have to restart and go back and fix this, but it might be that this position is slightly off. So you could try and turn this on. It'd be better if we had the card in front of us in this case, because it'll tell us exactly what to use for, I think, all these things. But if you were trying to actually refine that position, then you would turn on XU, and that would allow us to refine both of those. Let's give it a shot because we've only got a minute or two left, just so you can see what this looks like. Might have gotten a smidge better. We might be getting close though. I'm still seeing some problems here. Like at the ends, it's underreporting, and the middles, it's sort of over-reporting. So let's look at some of these where it's getting it wrong in the middle and see what they're doing. Yeah, it's just not quite intense enough. This almost makes me think that there's an impurity there. Let's see, something you can do if you want to determine, like, should there be a peak present? If you go back to the home button, there's this K button here. This stands for key press list. There are a bunch of different buttons here that will toggle on and off different things. Like, for example, if I want graphs, I hit G and it'll put graphs on it. Or if I want, like, if I hit I, let's see, is it Q? Yeah, if I hit Q, then it plots it in Q space as opposed to 2 theta space, and Q will toggle between those two. One thing you can click is A. I think it's A. That might only be if you have multiple phases. No, it is. If you hit A, check it out. It produces a legend where it'll show me my observed calculated background, but more importantly, it'll show you this little tick mark. See that vertical tick mark, which corresponds to the lanthanum hexaboride phase? You can zoom in on some of those where we thought we saw something. Like, let's go back to our magnifying glass. And when I zoom in on this, it's looking okay. Where was it that I thought I saw something? Yeah, if you thought that there was like another little bump there, what this is telling you is that there's not, we don't expect to see a lanthanum hexaboride peak there. So if something's going on there, maybe it's picking up something from the holder, or you had an impurity present that you didn't realize when you loaded it in there. You accidentally spilled something in there. I'm not seeing anything too dramatic here, but this will be really important on our next sample where we will see that there is an actual issue to worry about. But for the most part, this is pretty good fit, right? Again, we got our error down to, we're at 8% or something. So even though it's not perfect, remember our rule of thumb is that a felt refinement is never complete. It is only abandoned. And at some point you have to say, like, I'm just going to abandon it, right? And we might be getting close to that point. If you feel like it's good enough, then at that point you'd come back over here to your data tree. And the most important thing that you would have is this information right here. You'll take down a piece of paper and you'll write those down. I think you can probably export it as well. Can you export the instrument parameter file? Maybe between now and tomorrow's class, because we're wrapping up right now, is I can look out how you can export the instrument parameter file. You can save it as or something. Or you can always just write it down. The point is that these values we're going to save because they represent the instrument shape. When you generate data with this instrument, you're always going to have, at a minimum, this shape, because this is as you have a standard that you purchase which has the narrowest possible peaks, which means the entire shape that you see here is primarily coming from your instrument. So if you then take out your standard and now you put your new sample in that you're going to investigate, a starting point for the shape that you should use should be whatever you got previously, including the zero, the UVW values, the spherical. That should be your starting point. You're going to further refine them, but that should be your starting point. And this thing you're not going to refine. You're going to leave that set. Once you know what the zero is, you're just going to leave it. Okay, that is our first day. So we're going to wrap up here. go ahead and end my screen share on the Zoom. So next time, end that real quick. So next time for next class, we're going to do some more examples of root belt refinement. We'll probably spend at least half the time for tomorrow's class doing a couple more examples. If you want to try this ahead of time, try the lanthanum hexaboride between now and tomorrow would be a good idea because you can come with questions. And then the final day, we're going to talk about, okay, let's say you finish your refinement and you're ready to try and interpret it in terms of Vesta and actually plotting the crystal structure and seeing what you've actually refined and how to plot that into nice figures. We'll cover that on the last day and a little bit of tomorrow. Okay. If you have questions between now and tomorrow, feel free to reach out to me via email. I'm going to drop my email in the chat here. It is
How about